All right, I'll show you a few more things now. First, we'll look at something called pKa. Now, you've already seen pH and pOH. pH is the negative log of the hydronium ion concentration, thus the H. pOH is, of course, the negative log of the hydroxide or OH ion concentration. So pKa is going to be the negative log of your Ka, your acid ionization constant. Similarly, there is a pKb, which is the negative log of Kb. But you'll primarily see pKa in use. Now, for organic chemistry, which a lot of you will be going into next year, whereas your general chemistry textbook has a table, in fact, there's a fairly lengthy table in the appendix with Ka values. Organic texts tend to have a table with pKa values. One reason for it is pKa is a convenient way to compare the strengths of two acids. You already know that lower pH means that there's more hydronium. Most students would say it as a lower pH means a stronger acid. Lower pH means a stronger acid. Well, lower pKa also means a stronger acid. So you can look up the pKa's of two acids and quickly, easily compare how strong they are. The one with the lower pKa number and your stronger acids tend to have pKa values that are negative. So they're very low. They are going to have stronger acids are going to have lower pKa's. All right, so that's how we do that, and we'll come back to that here shortly and use it in something. Next thing I want to talk about is buffers. So buffers are, how do I want to put this? Substances that resist a change of pH. They resist a change of pH. My intention is to do a demonstration of this for you. It's something we normally do in lab, but I will hopefully make a video of that soon and probably post it as a lab for you to record some information about it. So buffers resist change in pH. They typically consist of a weak acid mixed with a salt, and that salt needs to contain that acid's conjugate base. So a weak acid plus a salt containing the acid's conjugate base. Cb, conjugate base. Sometimes you'll hear it simply stated as a weak acid and its conjugate base. But the conjugate base is an anion, and you cannot go to the shelf in the supply room and pick up a bottle of anions of any sort. Anions must have a counter ion, a cation with them, and when you put a cation with an anion, you salt. So as an example, we might take acetic acid and sodium acetate. I'll just do the simple formula for that. So that combination will create a buffer, and it will hold a steady pH. That particular one, the pH could range anywhere from a little bit below 4 to just below 6. And we'll talk more about that here in a minute. So let's let me see if I can find an example, and if not, I'll just go with this one and make something up. All right, so here's a problem that gives us a mixture of ammonia and ammonium chloride. Now, this one I didn't really address. This is another possibility. Up here I said weak acid and a salt with its conjugate base. You can also use a weak base and a salt that has its conjugate acid. So it can go either direction. So what we have here is ammonia, which is a weak base, and ammonium chloride, which, as we have seen before, is a salt formed by the reaction of ammonia with hydrochloric acid. So this ammonium chloride will separate when it dissolves into ammonium ions and chloride ions. In other words, the ions will dissociate. So let's see, in this particular problem they told us that the ammonia was 0.2 molar and the ammonium was 0.3 molar. Now I want to do this I want to add a step to this just to reinforce something we've already seen. So first thing I'm going to do is let's look at what ammonia does when it reacts with water. Now, the ammonia is going to accept a proton from water. So water is going to act like an acid. It's going to give off a hydrogen. And that hydrogen, which will be positively charged, a hydrogen ion will move over and bond to the unshared pair on the nitrogen in ammonia. So that's going to give us ammonium, and it's going to leave hydroxide from the water. So that lets us see that this is a base. Okay? This accepted a proton. It provided a pair of electrons for the acid to bond to, the hydrogen to bond to. Again, the term that's universally used is donated the pair of electrons, but again, I don't like that word, but that's okay. It's not up to me. So let's first do this with no ammonium chloride. What if we just had 0.2 molar ammonia? When we first put the ammonia in the water, there is no ammonium, there is no hydroxide. Actually, we know that there is a tiny amount of hydroxide just from the water itself, but negligible, ignorable. All right, so this is going to go down by x. We're going to add x of this and x of this, so that at equilibrium we have 0.2 minus x, we have x, and we have x. And Kb for ammonia is, I'm going to have to look that up. All right, so it's 1.8 times 10 to the minus 5. And so it's going to equal x for the ammonium times x for the hydroxide over 0.2 minus x. And we'll say that that minus x is negligible. Ignore it. And so that's going to give us 3.6 times 10 to the minus 6 equals x squared. And square root of 3.6. I don't know. 3.6 times 10 to the negative 6th square root X is 1.9 times 10 to the minus 3. And that would give us a pOH of the log, change the sign, 2.72, and therefore the pH would be 11.28. Okay, now all of this is saying that if we just had 0.2 molar ammonia. All right, now we need to do that again. This time we're going to include the 0.3 molar ammonium. Remember, if one ammonium chloride comes apart, we get one ammonium and one chloride. So when 0.3 molar ammonium chloride dissociates, we get 0.3 molar ammonium. So we're going to do this all over again. We're going to say NH3 plus H2O. We're going to get NH4 plus and OH minus. And this is going to start at 0.2, but this is going to start at 0.3. So, and this starts at 0. So this goes down by X, this comes up by X, this comes up by X. And at equilibrium, we're at 0.2 minus X, we're at 0.3 plus X, and we are at X. And so our 1.8 times 10 to the minus 5 equals 0.3 plus X times X over 0.2 minus X. As usual, we're going to say, when you subtract X or you add X, it doesn't really change the number you're adding or subtracting it to or from. So now we get 3.6 times 10 to the minus 6 equals 0.3x. And that means that x is going to equal 3.6 times 10 to the 6 minus divided by 0.3, 1.2 times 10 to the negative 5th. Which in turn means, people ask sometimes, this symbol 3 dots means therefore or so. Alright, 1.2 times 10 to the minus 5th equals x. Therefore, since x represents hydroxide concentration, pOH is the negative log of that, 4.92. And that leaves the pH at, what is that, 14 minus 14, so 9.08. So, if we just put ammonia in water, and we don't put any ammonium in there, then that'll create a pH of 11.28. That's pretty high. That's basic. But if we add its conjugate acid in the form of this salt, ammonium chloride, to a level of 0.3 molar, then the 0.3 molar ammonium is the common ion. Okay? Dissolving the salt produced this ion. Reaction of the ammonia with water produced this ion. This ammonium ion is common to both of the reactions happening in the same container. And remember, the common ion effect will do just that. It will affect the equilibrium per Le Chatelier's principle. So since we're putting more of something over here, it drives equilibrium back to the left. we don't make as much hydroxide. And that's what bases do. Bases make hydroxide. Okay? So the pH does not go as high. And what we have here with this mixture of these two things is a buffer. This one consists of a weak base and its conjugate acid. And this will hold the pH very close to 9.03. If you were to add an acid to it or a base to it, the pH isn't going to go down or up significantly because of this combination of ammonia and ammonium chloride. The ammonia, being a base, would be able to react with any acid that's added. The ammonium, being a conjugate acid, would be able to react with any base that is added. Now, buffers are hugely important, particularly in organic and more particularly in biochemistry. In a later video, I want to show you about the bicarbonate buffer. That is one of the main things that keeps the pH of your blood where it is supposed to be. And if your blood pH moves very much, say by even 1/10 of a pH unit in either direction, up or down, you are in serious trouble. So buffers are hugely important, particularly to life. Next thing is, so what we've done here, what we've done right here in the bright green, is we have calculated the pH of a buffer the way we already know how, which is using a rice table. And some call it ice, some call it rice. If it's rice, R is the reaction, the equation for the reaction. All right, so we already knew how to do that. But for buffers, there's actually a shortcut. And that shortcut involves something called the Henderson-Hasselbalch equation. Some pronounce it Hasselbalch. I believe it's Hasselbalch. It's not Hasselbeck. I hear it called that sometimes. So earlier we had looked at pKa, and I told you we'd come back to it. Well, here it is. The pH of a buffer is equal to the pKa of your conjugate acid plus the log, base 10 log, of the base over acid ratio. Okay? Give you a second to copy that down. Okay, so pKa. All right, so for this, the acid is ammonium, and you cannot look up Ka for ammonium. You can, however, get the Kb of its conjugate base, which is ammonia, and conveniently we already had that. The Kb for ammonia is 1.8 times 10 to the minus 5. So let's recall that the Ka of a conjugate acid times the Kb of its conjugate base always equals Kw. Kw is always 1 times 10 to the minus 14. The Kb here is 1.8 times 10 to the minus 5. So to find the Ka, we're going to take 1 times 10 to the minus 14, divide it by the 1.8 times 10 to the minus 5. And that gives us a Ka of 5.555555. The 5's go on forever. Times 10 to the minus 10. All right. So the Ka right here for ammonium is 5.5 times 10 to the minus 10, because the Kb for ammonia, its conjugate base, is 1.8 times 10 to the minus 5. So how do we get the pKa of that? Therefore, the pKa is, we need the negative log of this number. All right. So just work through that again. 1 times 10 to the negative 14. Got a bad glare there. You can't see my... How about that? There we go. So 1 times 10 to the negative 14 divided by 1.8 times 10 to the 5 negative is 5 point repeating 5s times 10 to the negative 10. We take the log of that and change the sign, and that gives us a pKa of 9.25. It's times 10 to the 0, and 10 to the 0 is 1. So in other words, it's just 9.255. I'm just going to call it, well, I'm just going to leave it in the calculator actually, but for writing it down purposes, I'm going to say 9.26. Now, we need the log of the base over the acid molarity. So the base here was ammonia at 0.2. The acid is the ammonium, which is 0.3. So we've got 0.2 over, in other words, divided by 0.3, which gives us 0.066666. I've got this in scientific notation mode. Probably shouldn't. Let's take it out of that. There you go. It's 2/3, in other words. Okay. The 6's go on forever. 0.2 over 0.3, that's 2 over 3, that's 2/3, 0.66666. Now, we need the log of that 0.2 over 0.3. We need the log of 2/3. So let's get the log of that. And it's negative 0.176. All right, so we've got 9.26 plus a negative point, I'm going to just say 0.18. How about that? All right. So what's 9.26 plus a negative 0.18? In other words, 9.26 minus 0.18? Well, that is 9.08. That's the pH of this buffer. By the way, that's what we got over here when we did it by the Rice method. How about that? So, 2 different ways to find the pH of a buffer. You can do it the Rice method, or you can simply use A of your conjugate acid and add to it the logarithm of the base over acid ratio. Now, if you get confused, is it base over acid or acid over base? And I've seen this happen many times down through the years. Here's the way to think about it. What is ammonium compared to ammonia? Ammonium, NH4, is the acid. I've got more of the acid. More acid should lower the pH. So the pKa is 9.26. By putting in more of the acid, that number should go down. And by putting base over acid, having 0.2 over 0.3, the log of that becomes a negative number. If I'd put the acid over the base, I would have 0.3 over 0.2, which is 1.5, and the log of that would be a positive number, and it would make this go up. So just use a little, dare I say, common sense. Since we're putting in more of the conjugate acid here, 0.3 is more than 0.2. More acid means lower pH, lower than just the pKa of the acid. Okay? All right. So that is it for about 3 different things there. Definitions of pKa and pKb, what buffers are, the common ion effect, shown again, how the ammonium ion, when added here, decreased the ionization of the ammonia, made us produce less hydroxide. We produced more hydroxide here than we did over here because of the common ion effect. This also then is how to calculate the pH of this buffer, because a buffer consists of a conjugate of a base and its conjugate acid, or an acid and its conjugate base. And then the shortcut method, the Henderson-Hasselbalch equation. All right, that's it for this one.